In this video, we are going to look at questions from section C of Science paper 2 for the 2017. Now, let's begin with the first question. On the packet of a particular beer is written, contains 5% alcohol per unit volume. So whenever we look at an opaque beer, we are looking at mostly the traditional alcohol that are made in Africa using starch. Now let's look at the first question here. Name the alcohol found in opaque beer. So this alcohol is ethanol. So this is the only alcohol according to science that can be made by fermentation from or using a starch. Now let's look at Roman number 1. So describe in outline how this alcohol you've named in A above is commercially produced from starch. So as long as we are looking at starch here, we are looking at the formation of ethanol. So I'm going to give my answers in point form. So the first step that must be done whenever they are making alcohol using the process of fermentation is this starch must be broken down into simpler molecules by heating the carbohydrate. So we'll say step number 1, heat the carbohydrate to break it into simpler molecules. So that is the importance of heating the carbohydrate in hot water. So we are just trying to break the complex carbohydrate into simpler molecules. Now let's look at the step that must be followed after we heat the carbohydrate. Then we need to add the yeast, and the reason why yeast is added, there is an enzyme zymase that assists the reaction to move at a faster rate. So point number 2 will say yeast is added to the mixture. So that is our second step. Then for the third step, we'll just say the yeast contains enzyme zymase, which speeds up the rate of reaction. So that is the importance of yeast. So in general, the yeast is just there to make sure that the reaction moves at a faster rate. Now, away from the yeast, the other thing that must be done is the mixture must be kept warm for several days. The mixture must be kept warm. So that is the point. So the warms must be made sure that it shouldn't be too hot or cold. So there should be a certain favorable temperature. And you may encounter a question, why is this mixture, why is the temperature of the mixture kept favorable? So that the enzyme, which is the zymase, can operate effectively. We know that if the temperature is too high, the enzymes might be denatured, and also if the temperature is too low, the enzymes might be are inactive. So to make sure that the enzymes are working at their rate, we need to make sure that the temperature is kept favorable. Then in the last part here, as the fermentation process is taking place, you need to make sure that from the beaker or the drum, whatever a bucket that you are using for this process, you need to make sure that you cover it to prevent air from entering the drum where the fermentation is taking place. And the reason why we need to keep air out is to prevent oxidation. So the air must be kept out. So these are the points that we can give according to the question. So we have written about 5 points according to the question. So the question had 5 marks, but when writing these, make sure you put them in S's. Then let's move on to Roman number 2. So Roman number 2, write down a balanced chemical equation for the formation of glucose. So first I'm going to write in the equation in weight, then from there we'll convert into a chemical equation. So we'll say sugar, we'll just say sugar, which is glucose. Then this should be decomposed, or if you want we can show water, but we'll just use sugar is equal to, then we need to add the yeast. The yeast, we know that it contains the enzymes. Then this will give us ethanol plus carbon dioxide. So the gas that is produced during the formation of ethanol by the process of fermentation is carbon dioxide. Now if you want to convert this in chemical symbols, the sugar has C6, H12, or 6. Then ethanol is C2, H5, or H, plus carbon dioxide we have CO2. Now let's see how we can balance this equation. So from the reactant side here, we can see that we have 6 atoms of carbon, but here we have 2 here plus 2 here. So let us put 2 here. So we can see that we have 2 carbon atoms here and 4 atoms of oxygen there. Then let's also put 2 here, so that if we know that if we multiply 2 times 2 will give us 4 plus 2, we'll have 6 atoms of carbon. Now let's check for hydrogen. Hydrogen on the reactant side we'll have 12 atoms of hydrogen, but here let's see, we'll have 2 times 5, 10 plus these 2 here, so we have 12 atoms of hydrogen. Let's check for oxygen. On the reactant side we have 6 atoms of oxygen. Then from this part here we can see that we have 2 atoms of oxygen. So 2 plus these 2 times 2 we have 4. So our equation is now balanced. So this is the balanced equation for the decomposition of starch into ethanol and carbon dioxide. Then let's move on to question B. Give one use and one bad effect of ethanol, of the alcohol found in beer. So this question is same as we want to give one use of ethanol and also the bad effect of ethanol. So one use of ethanol, it is used as a fuel. So if we use this one as a fuel, we know that if we react ethanol plus oxygen, that is combustion, so energy is produced, then the product we are going to have water and the carbon dioxide. So the negative impact of carbon dioxide is it may cause global warming. So it may cause global warming. So that is the bad effect of alcohol, using it as a fuel. So it depends, but if the same alcohol used as just the alcohol as in drinking, the negative effect it may, if it is consumed in a large quantity, it may result in lack of coordination, like drowsiness. So that is the other negative impact. But I've answered the causative of this alcohol in global warming because of my answer, the use as a fuel. Okay, so now we move on to question C2. A piece of magnesium ribbon was meant to react with dilute hydrochloric acid. The volume of the hydrogen gas collected in a syringe was measured at time interval. The results are shown below. So here we have the setup where they are reacting magnesium with excess acid here. We can see the excess acid here, then the magnesium. So this is where the reaction is taking place. Now we also have the stopwatch. The stopwatch is used to measure the time taken for the initiating of the reaction up to the completion of the reaction. Then so from this diagram here, we can see that at the beginning of the reaction, the reaction was fast, but as time progressed, the reaction started to drop until it stopped, since the reactant, one of the reactant was completely used. Now let's look at the first question here. Write a balanced chemical equation for the reaction between hydrochloric acid and magnesium. So there was a condition that including the state symbol. So first, as for me, I like first beginning by the word equation. So we are trying to construct an equation between a metal. So here we have a metal reacting with an acid. So what are we supposed to have in mind whenever we see this type of reaction? We know that the first one, we are going to have salt plus hydrogen gas. So the hydrogen was the gas that was being collected in a gas syringe. Now let's look at what is our metal used here. The metal is now magnesium plus hydrochloric acid So now the salt is an ionic compound, so it will consist of the metal. So do not change anything with the metal, but from the acid, depends on the acid that you have used. If the acid used is hydrochloric acid, you need to add the chloride. So that's a pattern. If it were sulfuric, you add sulfate. Nitric, you add nitric. Then plus hydrogen gas. Now let's convert this into state symbols. So the magnesium is Mg. Magnesium is solid plus hydrochloric acid, HCl aqueous. Then for us to write the chemical formula for magnesium chloride, we need to put the valences into. So magnesium is in group 2, so it has a valence of 2. Chlorine is in group 7, so it has a valence of 1. So if we use the cross method, we are going to get magnesium chloride as MgCl2. So this is what we are going to have here, and magnesium chloride is a soluble salt, so here we are going to have aqueous plus hydrogen. Hydrogen is the atomic molecule. Now the remaining part here, we need to balance this equation. So from the product part, we can see that we have 2 atoms of hydrogen, while 1 atom of hydrogen from the reactant side. So what are we going to do? We need to put 2 here. Now this 2 is also affecting chlorine, so we can see that we now have 2 atoms of chlorine, also 2 atoms of chlorine. So our equation is now balanced. Okay, so now we move on to question B. So we have the results, time in minutes. So then the volume of hydrogen. So when the time was 0, no volume was produced, 0.5, then we have 80 cubic, 1.014 up to 40 here. So the question is, we want to plot a graph of the results, volume against time. So volume will be in y-axis, then against, this is our against time, so the time should be in x-axis. Now for science is different from mathematics. In mathematics, we are given a scale that we are supposed to use, but under science, we need to make our own scale. So when making a scale, let's begin with the x-axis. So we can see that we are beginning from 0 up to 6.0. We can just say up to 6 there. So what number can represent the 2 centimeters on the graph paper, so that we can cover these numbers up to 6. So if we use let's say 0.5, it won't fit on the graph paper, but let's use 1. So say so for you that are using the actual graph papers, make sure 2 centimeters on the graph paper on the x-axis represents the 1 unit. So we'll say here we have 1, 2, 3, 4, 5, 6. So the key is I've reached at 6. If I want, you can reach up to 7 or 8. The key point is as long as the last number is covered. Now let's go to y-axis. So the y-axis, the lowest number is 0. Then we want to have numbers up to 40. So you can use 10, 20, 30, 40. You can use 0, 5, 10, 15, 20. As long as the graph is fitting those numbers, that is okay. But I'll use 10 here. So 10, then we have 20. Here we have 30. Here we have 40. So now, after we are done putting the numbers on the graph paper, let's begin now drawing. So since I'm not using the actual graph paper, so I'll try my level best to make it accurate. But for the viewers, please make sure you use the graph paper so that you may have a clear picture here. So the first pair of coordinate is 0, 0. So 0, 0 is here. So this is the origin of the chemical reaction. Then the second one is 0.5. So 0.5 is half of 1. So this is here, somewhere here. This is our 0.5, 8. Now, if you are using the scale of 2 centimeters to represent 10 units on the y-axis, those small boxes represent 1. So you need to count 1 up to 8. So this is where, somewhere here is where my 0.5, 8 is. Then we move on to the next one, 1.0, 14. So you go on the x-axis 1, then you have 10, So then you just need to add 4 smaller boxes, so it is somewhere here. Then we move on to 1.5, 20. So 1.5, 20 is somewhere here. Then we go to 2, 25. So 2, 25 is somewhere here. So it's between 20 and 30. Then we have 3. We have 2.5, 35. So 2.5, 35 is here. Comma 35 is here. Then we have 3, 33. So 3, 33 is here. So this indicates an error. This indicates an error, but let's just leave it like that. So 3 point, I will circle it. This means that if we are to draw like this means that the reaction is fast, then it becomes slow, and it also speeds up. So we'll see what we would look at this point here. Then let's move on to 3.5, 36. 3.5, 36 is somewhere here. Then 4, 38 is somewhere here. Then we'll have 38, 3.5, 36C. Then 38, 4, 38 is here. Then 4.5, 39, somewhere here. Then 5, 40 here. 5.5, 30 here. 6, 40 is here. So we can now connect these points. So this is my graph, the sketching of my graph. Now this point here has an explanation. So the actual point, this was supposed to move in this direction like this. So we move on to question C. Which result should be rejected as being an error? So the result that should be rejected as being an error is this point here. So this is our error, and the reason is we can see here the reaction is moving up, then it comes down here. So we cannot say that the reaction was moving, at a greater speed, then it decreases and it also starts to increase. There is no such thing. When the reaction is moving, it will keep on moving until it started to slow, until it is at a same speed. Now let's first analyze this point. We need to check carefully what of this is our error. So let's look at how can we answer this question. So let's look at for the numbers from the table. So we have 20, 25 here, 35, 33, 36. So this point is very crucial. We need to take time for us to think. So according to my observation, I don't know if it's my graph, but I think the error was this point here, because if we are to draw this line, we can see that the way it is moving. So this is how the reaction was supposed to move. So this is our error here. So we move on to question D. What was the maximum volume of hydrogen produced in this reaction? So from the table, we can see that the last number was 40. So here we have 40, here we have 40, here we have 40. So after we reached at 5 minutes, the reaction stopped. So even if the reaction stops, the time keeps on moving. This is what the indication here. So whenever you are trying to find the maximum volume of a gas produced given a question like this one, just look at the last number. So the last number or the numbers at the last where the numbers stopped to change. So the numbers stopped to change at 40. So this was the highest number here. So 40 cubic centimeters. So we know that even from the graph here, we can see that our graph, this line never exceeded this point. So this is another indication that was the maximum volume. Then if from the graph, how can you tell when the reaction came to an end? So from the graph, we can see that here it was more steeper. It was steeper. So at this point, the reaction was very fast. Then the reaction somewhere here was just fast. Then here the reaction was slow. Then at this point, when the graph started to move parallel to the x-axis, the reaction stopped. So we can tell from the graph when the graph started moving parallel to the x-axis. So when the graph started moving parallel to the x-axis. So this is an indication that we can use. So at this point here, this is the indication that the reaction has stopped. Then F, what is the average rate of the reaction? So here, the average, what we are going to do is, let's find at least 3. So the first average here, we have change in volume over change in time. So we'll find, let's pick this point here. This is our first point. We know that time is 1 minute. Then when time was 1 minute, the volume was 14. So we have 14 over 1, which is 1 into 14 will give us 14 cubic per minute. So for 14 cubic centimeters per minute. This means that at this point, every 1 minute, 14 cubic centimeters of hydrogen was produced. Let's also find another point here. So let's find it here. So this will be our average is equal to change in volume over change in time. So the time here is, so we can see that we have 3. Then the volume here is 33. So if we divide 33 divided by 3, we get 11. So 11 cubic centimeters per minute. So you can see that at this point, I'll call this as point A. 14 cubic centimeters was produced per minute, but at point B we can see that there is a reduction here. Here 14, instead of 14 we have 11 cubic centimeters of hydrogen was produced per minute. So you can see that as the reaction proceeds with time, the speed of reaction decreases, and we can see this by the result that is being produced. Now let's check, let's take this point C. You can also find the average here. So rate of a chemical reaction, or let me not say average, so this is the rate. So rate at C will be the time at C, will get 4.5, then by 39. So if we divide the 39 divided by 4.5, so I'm getting almost 8.9. So we can see how the speed has decreased. So at this point, 8.9 cubic centimeters of hydrogen was produced per minute. Now for the average, so for the average, we are going to add these three here. So average is like the mean. So 14 plus 11 plus 8.9 over 3. So 14 plus 11 plus 8.9. So I'm getting 33.9 over 3. So now divided by 3, I'm getting 11.3. This is our average. So 11.3 cubic centimeters per minute. Okay, so now we move on to the last question, question 3. Iron 2 sulfate crystals can be prepared from the reaction between iron metal and warm dilute sulfuric acid. Construct a balanced chemical equation for the above chemical reaction. So let's begin with our word equation. So we have a metal here plus the acid. So metal plus acid, we get salt plus the hydrogen. Then the metal is the iron plus the acid is sulfuric acid. So the salt here we have been given its iron. So from the sulfuric acid we get sulfate plus the hydrogen gas. Now iron, the symbol is F, solid. Sulfuric acid is H2SO4 aqueous. Then iron 2. So since we have been given this number 2, this means that we are using the iron with the valence of 2. So iron has a valence of 2. Sulfate has also a valence of 2, so we can just cancel these. So we have iron, sulfate, aqueous. It is soluble. The reason I've written aqueous because it's soluble, plus hydrogen gas. So we can see that our equation is balanced. We have one atom of iron, even here 1. Then 2 atoms of hydrogen, also here 2 atoms of hydrogen. Then 1 atom of sulfur, 1 atom of sulfur, 4 atoms of oxygen, 4 atoms of oxygen. So this is our chemical equation. Then Roman number 2, what is the importance of warming the acid? So the importance is to initiate So to initiate the reaction and to increase the speed of the chemical reaction. So this is the importance of why the acid must be warm for the reaction to start and also for it to move at a faster rate. Then how do you ensure that the iron 2 sulfate obtained is free of sulfuric acid? So this reaction of this dilute sulfuric acid with iron metal. So our aim is we want to produce the iron sulfate and hydrogen gas. Now, if we want to have a salt that is free of sulfuric acid, so how can we get rid of sulfuric acid? So we need to make sure that when reacting, the ion must be in excess. Why? So that all the acid can be used up. Then if there is the remainder or the remaining of iron, it is easy to remove the iron metal from the salt. We can just filter that. So by making sure, we'll say by making sure that iron is in excess. So is in excess to make sure that all the ions of the sulfuric acid are used up. That is what we can do. Now let's look at Roman number 4. Describe how you can obtain pure crystals of iron 2 sulfate from the above reaction. So I'll give this in point form. So the first one, the impure salt that we have, which is iron sulfate, the first one is you need to dissolve it in order. So number 1, dissolve the iron 2 sulfate in water to form a solution. That is our first step. Then number 2, heat the solution. Heat the solution so that some of the water molecules can evaporate. So when heating, don't heat all the water molecules. We want some molecules of water to remain so that they can form the crystals. So you just have to heat a certain amount of water molecules so that they can evaporate. Then after those water molecules are evaporated, then you need to cool. So it has to be cooled. So after the cooling, then the crystals will be formed. So say then cooled, then cool the remaining solution so that it can form crystals. So this is how we can move about this question here. Okay, so now we move on to question B, the last one. When an iron nail is placed in aqueous solution of copper 2 sulfate, reaction takes place. Construct an ionic equation for the reaction. So we have iron plus copper 2 sulfate Now for this reaction to take place, we need to make sure that the metal that we are using here is more reactive than this one in a compound. So iron will displace copper, giving us a iron, we'll say iron 2 sulfate. So this is a single displacement plus C. Then the copper will remain alone. Then the symbol for iron is F, solid, plus copper here is Cu, SO4, aqueous. Then we have iron, sulfate, aqueous, plus the copper here solid. Now when breaking stuff into ions, make sure you just break those in aqueous solution. So the iron will be just in its natural state. Then copper will have a positive 2 aqueous. Sulfate will also have now a negative 2 aqueous. This time iron is part of the compound, so iron will have a positive 2 aqueous, plus the sulfur will have a negative 2 plus copper. So let's get rid of the spectator ions. So the spectator ions are those in the same state before and after the reaction. So we can say that sulfate is a spectator ions. Then our net ionic equation will write the remaining of these. So we'll have F solid plus copper positive 2 aqueous. Then this will give us iron with positive 2 aqueous plus copper solid. So this is our net. So this is our net ionic equation. Then this is just our ionic equation here. Then let's look at state to observation would make during the reaction. So to observation, the solution would turn light green from blue. Then the second one, the iron nail would develop a reddish browny color. So this is how we can answer. So, and that's it for this video. Thanks for watching.